So in continuation of my previous video, let us discuss about refrigerators, as well as freezers. So according to second law of thermodynamics, heat can spontaneously flow from hot to cold. So this is possible. Heat can able to flow from hot to cold. It is a natural and spontaneous process, but slow process. Secondly, the reverse is not possible. That is, heat cannot flows from cold to hot region. This is not possible. But we can make it possible by introducing a heat pump. By introducing a heat pump in between cold and hot reservoirs, you can make heat to flow from cold reservoir to hot reservoir. So you can make possible the impossible into possible. So for that we use air conditioners, air coolers, refrigerators and freezers. Actually, freezer or refrigerator is a cold reservoir. From the cold reservoir, heat is expelled to the hot or warmer kitchen. So for that, this is made possible only by means of using heat pumps like compressors and all other instruments. So by using those instruments, we can able to transfer heat from cold reservoir, that is refrigerators and freezers, to the hot reservoir, kitchen or laboratories. Similarly, in the first case, that is hot to cold, heat naturally flows. It is a natural process but slow process. In that case also, you can speed up the process by introducing a heat pump in between hot and cold reservoirs. So to speed up this process, heat pump can be introduced, or heat engine. More correctly, heat engine can be introduced between hot and cold reservoir in order to speed up this natural process. To speed up, we need to use heat engine. And one very good example of heat engine is automobile engines. We can say automobile engines, and also power generators, electric power generators. So one scientist, Carnot, name is Carnot, C-A-R-N-O-T, Carnot, predicted efficiency for these engines. according to his theoretical heat engine, for his theoretical heat engine, maximum efficiency E equal to work done divided by T hot. So T hot minus T cold. Here T suffix H means T hot reservoir. T suffix C means cold reservoir. H means hot, C means cold reservoir. So the efficiency equation, we can also multiply it with 100. So Carnot's maximum efficiency for his theoretical engine, heat engine, is possible only when temperature of cold reservoir reaches 0 Kelvin. 0 Kelvin. So when temperature of cold reservoirs reaches 0 Kelvin into 100, what you will get? TH by TH into 100. So 100. So maximum efficiency is theoretically possible for his Carnot's theoretical heat engine. So according to him, in real life, all the heat engines or all the heat pumps must have smaller efficiency than the Carnot's predicted theoretical Carnot's engine. So all the all the engines in our day-to-day life must have lower efficiency than the Carnot's engine. And also one more thing is, and lowest possible efficiency according to Carnot is, it will happen only when TH equal to T cold, when the temperature of the engine and the temperature of the ambient atmosphere are same. In such situation, 0 by TH, efficiency will be 0. And according to Carnot's equation for his theoretical engine, 0% of efficiency will happen only when temperature of hot reservoir equals temperature of cold reservoir. So when the engine's temperature and the ambient temperature are equal, then the efficiency of the engine will be automatically, it will be 0. So these two cases, in both these cases, temperature is only 1. There is no variation of temperature. There is no initial final temperature. So in both the cases, change in entropy is 0. So in both the cases, it is possible only for reversible process. Only for reversible process. But in real life, all the engines are working at room temperature only. According to Carnot's maximum efficiency, it is possible only when the ambient temperature goes to 0 Kelvin. But we are not working with 0 Kelvin. We are working with room temperature. But our real life engines, cannot show maximum efficiency. They always exhibit smaller efficiencies because our ambient temperature is at 300 Kelvin. So it is not possible for real engines. So in the case of real engines, the actual values of actual values of efficiency of heat engines can be for example heat engines, heat pumps, refrigerators, freezers, as well as freezers, so the equation of Carnot's efficiency, maximum efficiency for an actual or real life engines can be written like this: efficiency is equal to TH minus T cooled divided by TH. And for heat pumps like air conditioner, air cooler, the equation will be, here COP means coefficient of performance. Here we use, instead of efficiency, we use the term coefficient of performance. Coefficient of performance. So COP for air conditioners equal to T hot divided by hot minus T cold. And in the case of refrigerators and freezers, you will get another equation, coefficient of performance equal to T cold divided by T hot minus T. So you must be careful with these differences. T suffix hot for air conditioner, T suffix cold for refrigerators as well as freezers. So you can use these expressions to know the actual efficiencies, of course, coefficient of performance for refrigerators. Okay. Okay, I will tell you the example at the end of the class. Now we will see. So in these examples, with these instruments, all these heat engines, like automobile, car engines, two-wheeler engines, electric generators, then heat pumps means air conditioners, air coolers, then refrigerators, freezers, all these instruments are working at room temperature. So here T suffix C will be 300 K. T suffix C will be, cold reservoir will be at 300 Kelvin. So proportionally you will expect more change in entropy in all the cases. Change in entropy will be, it will not be equal to 0. So it will be, change in entropy is not 0. So change in entropy is a huge value in all the cases. It means most of the energy is dissipated as heat. Most of the input energy, heat energy given to these instruments, various instruments, is dissipated as heat. So entropy will be very high, so that efficiency will not be equal to that of the any Carnot's predicted efficiency. So efficiency of real engines always very much smaller than the Carnot's predicted efficiency for actual engines. I will tell you the example at the end of the class. Now we will see how refrigeration takes place or cooling takes place in a freezer or refrigerator. So in a freezer or a refrigerator, or freezer, actually there are four important segments for a refrigerator. One is condenser. Then throttle valve. This throttle valve is nothing but Joule Kelvin experiments porous part. Then there is a evaporator. Compressor. All these are all four important segments of a refrigerator. Nowadays, refrigerator or conventional refrigerator or freezers, four important parts. As you know, we use Freon gas here. All refrigerators use Freon gas. So when Freon vapors are compressed here, you will get a super saturated Freon vapor will be coming out of the compressor and it will be passed through the condenser. The condenser it loses the supersaturated Freon vapor, losses heat energy to the outside environment. It may be kitchen or any laboratory. It may be a kitchen or it will be usually kitchen or laboratory will be, or a room will be warmer than the refrigerator or freezer because this entire setup is cold setup, and outside part kitchen or laboratory will be very warmer than the cold refrigerator or freezer. So when the supersaturated Freon vapor reaches condenser, it loses energy, gives up energy or expels heat energy to the warmer kitchen because of the compressor's power, and now it is it becomes super saturated liquid. Freon becomes super saturated liquid form, reaches liquid, transforms to liquid form, and when it is allowed to expand through the throttling valve, so this is equivalent to the porous plug of Joule Kelvin's experiment, and here it expands by cooling. So liquefaction takes place. After throttling, Freon gas cools down, so its temperature decreases. In such a way it is liquefied. So Freon liquid, liquefied Freon plus Freon vapors. Vapors goes to the evaporator segment. In the evaporator segment, there may be some products inside the refrigerator or freezer, and these substances or grocery items may be there. These grocery items will be at ambient temperature initially. Since the temperature, that is grocery items or fruits, for example, fruits or chemicals inside the refrigerator. So naturally they are at higher temperature, so heat flows from high temperature fruits and chemicals to the liquefied, because this in these channels liquefied freon is allowed to pass through it. It is in immediate contact with this compartment. So heat naturally flows from fruits and chemicals to the evaporator segment, where it liquefied freon and vapors of freon absorbs those heat energy and evaporated. So finally freon vapors are formed. Freon vapors are formed, and these freon vapors again reaches the compressor, and in such a way the process is repeatedly takes place. So here it loses heat energy, it gains heat energy and becomes a freon vapor, and it is again compressed and again reaches supersaturated process, and this process completely takes place. And at here in the condenser zone, again the freon vapors loses heat energy to the warmer kitchen. So some amount of Q will be expelled to the warmer kitchen or laboratory. So in this process again some temperature will be reduced at here. Again cooling process takes place after reaching throttling valve. So again liquefaction takes place, and the temperature of the, so by means of repeated process, temperature of the evaporator segment will be maintained at minus 20 degrees Celsius. It regularly takes some heat energy and its temperature rises. Then again its temperature of the freon goes down by means of liquefaction, and in such a way minus 20 degrees Celsius or minus 10 degrees Celsius, whichever may be, the set temperature will be maintained by means of continuous expansion and compression of freon. Okay, so this is how a refrigerator or a freezer works. So if you look at the efficiency of such a, if you look coefficient of performance of such a refrigerator, of coefficient of performance, I suppose it is a refrigerator or freezer, and this is your kitchen. Now this is the compressor. Actually the main engine is compressor. So heat flows from cold reservoir T suffix C to hot reservoir kitchen. Heat flows in this direction. Actually some input is given to electrical input. Electrical input is given to the compressor. Imagine it is about 15,000 joules of energy. 15,000 joules of energy is given as input energy to operate the compressor, and also the ambient temperature of the laboratory or kitchen is room temperature here, So it is about 300 Kelvin. T is about 300 Kelvin, and refrigerator temperature is about minus 20 degrees Celsius or 250 Kelvin. 250 Kelvin. Now, to make you understand the importance of Carnot's theoretical possible performance and actual performance for an engine, how to compare, that is COP Q by QX minus C. So it draws 15,000 joules of input heat energy, that is compressor draws, and out of 15,000 joules of energy, for example, it utilizes only 5,000. Only 5,000 joules of energy is utilized as an example. So here 15,000 is QH and 5,000 is used properly as Q suffix C. So 5,000 joules divided by 15,000 joules minus 5,000 joules. So what you will get? 5,000 joule divided by 10,000 joule. So finally 1 by 2 joules or 0.5. So COP is coefficient of performance of this real engine, actual, or you can say actual coefficient of performance of refrigerator or freezer is 0.5. If you compare, if you want to know what is the maximum coefficient of performance according to Carnot's theorem, so this is the actual value of COP, and what is the maximum COP for that, or Carnot's maximum possible COP for any real engine. Carnot's maximum possible coefficient of performance for any real engine. For that you have to replace, instead of Q heat, you have to replace it with temperature. So what is the cold reservoir temperature? It is minus 20 degree. Your freezer is at minus 20 degrees Celsius or at 250 Kelvin. 250 Kelvin. So instead of joule I use Kelvin because temperature, we are dealing with temperature. The denominator will be like this. What is the TH? It is kitchen or laboratory temperature. That is 300 K, room temperature. 300 K minus 250 K. So what you will get? $250K by 50K. So about 5 times. So 5 is the Carnot's maximum predicted coefficient of performance is 5 for these conditions. So maximum, irrespective of the model of the compressor, irrespective of the model of the compressor or irrespective of the model of the refrigerator or freezer, Carnot's predicted maximum coefficient of performance must be 5. It cannot, any real engine cannot exceed this value. This is the maximum, okay, under these conditions, under these temperatures. That is minus 20 degree or 250 Kelvin and room temperature. And you can get actual value as 0.5. You can see the difference. 0.5 is the actual COP, but 5 is the maximum COP as per Carnot's theorem. So what does it mean? Only 10% of 5 by 0.5. Only 10% of the input energy is efficiently used for the cooling process or to sustain cooling of the refrigerator or freezer. Remaining 90% of input heat energy is dissipated as in different form, as heat or as a compressor sound, and it may have heat warmed up the environment. So all these things, so because it contains many moving parts, many mechanical parts. This compressor contains many moving and mechanical parts. So most of the energy is dissipated and lost. So the entropy for this kind of instruments would be naturally del S. Change in entropy del S will be very huge. Okay, because almost 90% of the input energy is dissipated as or lost. So change in entropy will be very high. So one can minimize, or one can bring this actual COP from 0.5 to close to Carnot's predicted maximum COP. Carnot's maximum COP only by reducing the changing entropy to nearly 0. So only by means of making as irreversible process to a reversible process, or a process which is having a maximum entropy of